In the second part of Lecture 13, we'll look at a different type of equilibrium problem that asks us how much to add or remove to a system at equilibrium. Here's our example problem. A reaction at equilibrium in a 500 ml flask contains 0.025 moles of H2, 0.025 moles of F2, and 0.268 moles of HF. How many moles of H2 must be added to get 0.300 moles of HF at equilibrium? So you might need to use this kind of calculation if you were designing a particular engine or reactor and needed a certain output in order to meet a specification or to keep the engine running at peak efficiency. So our method to solve this is to write a reaction table. Now, most of the time, you're accustomed to the unknown X in the delta row. But since we are trying to find out how much to add, we need to put X in the initial row. Since we know one equilibrium concentration, we can figure out the values on the delta row, calculate the equilibrium row, and use the K expression to solve for X. So first, kindly notice that we are given Kc, which is in units of molar. Here is our balanced reaction. Since I am asked how many moles of H2 must be added to get my target amount, I think it's a good idea to work my reaction table in moles. So I have my initial concentrations and my variable in the initial row because I'm asking how much H2 to add. Adding to the reactant, of course, drives the reaction forward. My target concentration of HF is 0.300. So knowing an initial and an equilibrium concentration of HF, I can make a deduction about the delta row. I know the difference between 0.300 and 0.268 is 0.032. So I know this value right here. Because of stoichiometry, the 2 to 1 to 1, I also know these delta row values, except of course I am going to subtract reactant and add product. So now it's a matter of bringing those values down to the equilibrium row. So the X travels with this. So we have 0.009 plus X, 0.009 and 0.300. Now that I'm ready to substitute this into Kc, I should divide by the volume of 0.5 liters. My Kc expression is products divided by reactants. And now I use my values for each of the materials. So you notice that 0.3 divided by 0.5 is 0.6, and that should be squared. My H2 is the 0.009 plus X divided by 0.5, and my F2 is, of course, 0.009 divided by 0.5, so that gives me 0.018, and I set that equal to my Kc value. Now it's time to process the math. So, of course, I'm going to cross multiply and try to get my X on just one side. So simplifying, I am now to this, and finally I solve for X, and the value is 0.0780 moles. I can substitute this back into my reaction table to see if it makes sense. So when I substitute that back into the table and get my equilibrium concentrations, they should certainly be equal to K. Of course, once again, we need to remember that if we're setting it equal to K, this is Kc, so we need to divide by the volume. And sure enough, we are back at equilibrium by adding the appropriate amount. So here is your question. How many moles per liter of carbon monoxide must be withdrawn from the equilibrium mixture below to triple the concentration of chlorine? I'm given a Kc value and initial concentrations. So I've added my initial concentrations, and I want to know how much must be withdrawn. So that means instead of adding X, I am going to subtract X right here underneath the carbon monoxide on the initial row. My goal is to triple the concentration of chlorine. So that means I am going to go from 0.050 to 0.150. Having the initial in the equilibrium allows me to figure out the delta row. Once I have delta for one of the materials, I can use it for the rest of the materials. Fortunately for me, the stoichiometry is 1 to 1 to 1, so that's easy. Notice that I am subtracting the COCl2 and adding to the product. That's because when I remove something, I am shifting this reaction toward the right. So when I bring all my math down, I have 0.4 of the COCl2, 0.15 minus X for my carbon monoxide, and 0.15 for my Cl2. I am working my table in molar, so I can directly use these values to solve for Kc. My equilibrium expression is products divided by reactants. So I substitute in my values from the equilibrium row of the table and set it equal to Kc. I trust you know to cross-multiply and rearrange, and I trust you're able to finish the solution from here. So notice some important things about the how much to add problem. Number one, the X that you are trying to add or remove belongs on the initial row. And number two, given an initial and one final, you can determine everything on the delta row, and therefore all your expressions on the equilibrium row.